All right. Let's take some time in get into some details why we finally can approximately represent a single pole transfer function body plot in that way. This is the mathematical representation of the magnitude of a single pole in the end, right? In this equation. Okay. So we can discuss this magnitude in two aspects. When the frequency is small or low, and when the frequency is high. When frequency is small, let's say very often it's small or large. Whenever you talk about small or large, or good or bad, or high or low, you always need a base. Okay, so here the base is omega 0 or f0. So if the frequency we're talking about is much smaller than omega 0 or f0, that's called small frequency or low frequency. In that case, we can see in the representation of magnitude, we can clearly see this item is going to be approaching 0 because frequency is omega is much smaller than omega 0. So therefore, approximately the magnitude in this case is going to be approximately equal to 1. Okay, so therefore, for the frequency range, when we're talking about the frequency range when it is much smaller than f0, for that part, the magnitude of a single pole transfer function is considered as almost equal to 1. Okay, and then the second part for high frequency part, that means when omega of f is much higher than omega 0, then in the magnitude representation, this item is going to be approaching quite high number, approaching 0 when omega is approaching infinite when omega is approaching infinite. Or, in other words, this second item is going to be much larger than 1. And therefore, the magnitude of this single pole transfer function will be approximately considered as only determined by the second item, because 1 is too small compared to the second item. So when you only look at the second item, the magnitude then is simplified to this representation as the frequency to the -1 power. Okay, as we discussed, the body plot for such form of transfer function will be a straight line. A straight line with a slope of -1 slope. Or -1 means -1 is an abbreviation or simple way to represent the slope. The actual slope is -20 dB per decade. Okay, every 10 times of frequency changing in the for every 10 times of frequency changing in the horizontal axis, the vertical axis is changing by 20 dB or decreased by 20 dB. That's the slope, minus 20 dB per decade. We simply call that as -1 slope. So therefore, in this case, when we are dealing with high frequency part of the transfer function, it's going to be approximately represented by another straight line with -1 slope. Okay, that's how we get this. So this two sections of straight lines at low frequency is flat straight line, or when the slope is zero, with zero slope straight line, and when frequency is high with -1 slope, these two sections of straight line is called asymptotes. Okay, so therefore we want to use these two asymptotes to approximately represent the single pole body plot. But then there's a question, and we need to discuss how much error there is between the asymptotes and the real body plot. Okay, you can see this is the actual, the bold curve is the actual body plot. These two sections of straight lines are the asymptotes, or the two sections of straight lines. Of course, there is differences. There is errors. The major error between these two is located in around the frequency range around the f0, around this f0 frequency, because around this range you cannot consider frequencies much smaller than f0 or much higher than f0, because in this range it is very close to f0. So all those conditions to simplify the magnitude of this transfer function are not valid anymore. So this is the major area that we have the error between the actual body plot and the asymptotes. If you get into detail, we found out that the maximum error is actually located exactly at frequency f0. You can calculate that the actual error at this frequency is going to be 3 dB. 3 dB is not a big problem, because 3 dB is very small. Okay, so therefore, in engineering, we very often just use these two sections of straight line, or asymptotes, to represent single pole transfer function, because the error is, the maximum error is only 3 dB. Okay. Of course, we have to memorize also there's phase, okay? Not just magnitude, there's also phase angle. The phase angle of a single pole, if you go back to the mathematical representation, of the single pole transfer function is this one, right? And the phase angle will therefore be represented it is exactly minus arctangent omega over omega 0. Okay, that has a picture of curve like this when, again, when you deal with very low frequency. Okay, when you deal with very low frequency where omega is much smaller than omega 0, and this item is going to be approaching 0. So therefore, the transfer function is just 1. Therefore, the phase angle is going to be 0 degree, approaching 0 degree. But when you deal with high frequency, when omega is much higher than omega 0, the second item is going to be quite large, much larger than 1. So the 1 can be neglected. So therefore, this high frequency would be simplified as a 1 over g omega, over omega 0. And that we know has, that real number, that complex number has a phase angle of minus 90 degrees, exactly minus 90 degrees. Okay? So therefore, for low frequency, the phase angle of single pole will be approaching 0 degree, for high frequency to be approaching minus 90 degrees. And in between, there is a gradual changing between 0 degree to minus 90 degree. And specifically, if you look at when frequency is exactly equal to F0, then omega over omega 0 will be equal to 1. Okay, and then the arctangent, minus arctangent of 1 will be exactly minus 45 degrees, exactly minus 45 degrees at this point. Then there's a problem. We still want to simplify this, because straight lines, we love straight lines. We don't like curves. So how do we use several sections of straight lines to approximately represent phase angle Bode plot? There are two options. Okay. One option is to use the low frequency, still this flat line, exactly at 0 degree, high frequency part at minus 90 degree, and in between we use the third section of straight line, but the third section straight line is the tangent line of this point. This point exactly located at F0 and minus 45 degree. The tangent line of this point. Okay, and then we extend that tangent line. It will be intersecting with the flat line at 0 degree, and also intersect with the flat line at minus 90 degree at these 2 points. And these 2 points can be calculated. We found out that the low frequency point, the low frequency intersection point is exactly F0 divided by 4.81, and the high frequency intersection point is 4.81 times of F0. This is good in terms that it uses the tangent line of at the point of F0. So therefore, there's no arrow. Okay, the approximation line has no arrow around, almost very small, almost no arrow around F0 area. Okay, that's the good thing. So therefore, the arrow around F0 is very small. But the bad thing is that this number 4.81 is very strange. This is a very strange number, not easy to memorize. Okay, so therefore there are somebody proposed another method for the approximation. They said, why don't we make it simple so that we just use these 2 points, one point at 1/10 of F0, okay, so that we use this as the intersection point, the low frequency intersection point, and then the other intersection at high frequency part is 10 times of F0, okay, and then we just connect these 2 points. That's going to be the third straight line we're talking about. Okay, that's very simple, much easier to memorize. So minus, I'm sorry, 1/10 of f0 and 10 times of the f0, these two intersection points. And you connect these two straight lines. A good thing is that that straight line will also pass through f0 and minus 45-degree point. Okay, and in this case, the arrows, although we cannot guarantee around f0 the arrow is approaching 0. Okay, we can see quite some arrow around f0 area, but we can guarantee that we can calculate how much is the maximum arrow. And maximum arrow is actually quite small, only 5.7 degree. Only 5.7 degree. Okay, so that's very small. So this is going to be the approximation of asymptotes we're going to use in the future. Okay, this 3 sections of straight lines to approximately represent the phase angle of a single pole. Okay. Then I'm going to quickly go through the rest of the typical transfer functions load plot. Single zero has a normalized form of transfer function in this way. Okay. 1 plus s over omega naught, omega 0. And the body plot of a single zero would be having magnitude for low frequency as a flat, or can be approximately represented as a flat line. But for high frequency, another straight line to approximately represent it with plus 1 slope, plus 20 dB per decade slope. Okay, you can imagine this asymptotes also has a maximum of arrow with the actual magnitude bode plot of about 3 dB. The maximum arrow is still only 3 dB, so very good approximation. And phase angle, at low frequency it is approaching 0 degree, at high frequency it is approaching plus 90 degree. Pay attention to this. It is exactly contrast with the single pole. Okay. Both for the magnitude bode plot and phase angle bode plot. And in between, we can use another straight line, the third straight line, to connect the point at 1/10 of f0 and 10 times of f0. And the maximum arrow is only 5.7 degree. Okay, that's single rail, single pole, single rail. But then there's, as I mentioned, a strange one. You might not see this before. It's called right half plane zero. Right half plane zero means this zero is actually located on the right half of the complex plane. The transfer function is really in this form. It's not like single normal zero is 1 plus s over omega 0. That's normal zero. Or single, when we say single zero. This string zero or right half plane zero is 1 minus s over omega 0. So therefore, the location of the this zero is on the right half plane. Okay, don't forget, when we talk about location of a zero, location of pole, we mean when we have this transfer function equal to 0, the root of this equation is called is where is leading us to the location of the zero or pole. Okay, so when you deal with this equation, have this transfer function equal to 0, you can solve for the root, and that root could be either located on the left half plane of complex plane or right half plane of complex plane. Basically, for what we talk about single zero, single pole, this normally seen zero poles are located on the left half plane. That means if this is the complex plane, horizontal axis is representing the real part. Vertical axis is representing the imaginary part. And then this is origin. Normal single zero single pole, they have a root of this equation located on the left half plane. Okay, we usually use a small circle to represent 0, a small cross to represent pole. This is their location on left half plane. But this right half plane 0 means it is located on the right half plane of the complex plane. Because this transfer function is 1 minus. Okay, if you solve that equation, that gives you a right half plane's root. Okay. You never seen this before, but you will see this in power electronics. So we'll talk about the real right half plane 0 in the real power converter. And the body plot of this right half plane 0 is kind of combining the magnitude body plot of a normal 0, but a phase angle body plot of a normal pole. You can see the upper picture shows the right half plane right half plane 0 magnitude body plot, and the lower part is the phase angle of a right half plane 0. You can see magnitude is the same as normal 0. For low frequency, it is flat, and for high frequency, it is changing to plus 20 dB per decade, or plus 1 slope. Okay, and for phase angle, this is at low frequency 0 degree, at high frequency minus 90 degree. That's the normal pole phase angle. Okay, so this is so different. Okay, pay attention to this. Right half plane 0 is quite different from normal 0, quite different from normal pole. Frequency inversion, I'm not going to get into details. It's, we almost seldom use it in our course, but you can go through the details of this part after the lecture. But I like to spend a few minutes on the combinations. That means when we consider the product of several transfer functions. For example, if a transfer function g sub 3 can be represented by the product of g1 and the g2, then how do we, let's see, either based on the transfer function, how do we get, based on the body plot of G1 and G2, how do we get the body plot of G3? That's one direction. Once we know the body plots of these single ones, how do we get the combined ones body plot? And there's also another direction of issue. We'll talk about that in the later on form. Because when we have this mathematical relationship, then suppose every transfer function can be represented in this way, in this polar form, polar coordinates form, or complex coordinates form. That means every transfer function can be represented by magnitude multiplied by the phase angle, by the exponential of phase angle. Then we will be knowing that for G3, the combined transfer function, it will be having a magnitude that is the same as the product of the magnitude of G1, G2. And the phase angle is also the same, but phase angle is the sum. Phase angle is not the product. Phase angle is the sum of phase angle of G1 and G2. Therefore, if we take the logarithm scale, you'll find out that in Bode plot, because in Bode plot we have to take a logarithm scale. In Bode plot, that means the magnitude Bode plot of G3 would be the magnitude Bode plot of G1 add up to the magnitude Bode plot of G2. So that means in Bode plot, if you have G1's magnitude Bode plot and G2's magnitude Bode plot, you just add them together. That's going to be giving you the magnitude Bode plot of G3. Because product in the linear scale, after taking logarithm scale, it becomes sum. Okay, so that's the magnitude. And phase angle is still sum, because phase angle Bode plot, we don't take logarithm. Phase angle Bode plot, vertical axis, we don't take logarithm. So therefore, the phase angle of G3 will also still be maintained as the sum of phase angle of G1 and G2. So therefore, for example, if I have a overall combined transfer function like this, let's see, it can be considered as, let's see, G0 divided by, not in this way, G0 multiplied by G1, G2, and where G1 is 1 over 1 plus S over omega 1, and G2 is equal to 1 over 1 plus S over omega 2. So the overall transfer function can be considered as a product of three things, three transfer functions. One constant, G0, one single pole located at omega 1, another single pole G2 located at omega 2. So let's see, we have the parameters of this omega 1, omega 2. As G0 is exactly equal to 40. 40 transfer to decibels is going to be 32 dB. You can calculate that. 40, you take logarithm, and then multiply by 20 is going to be 32 dB. And omega 1, let's see, omega 1 in the normal frequency, that means angular frequency omega 1 divided by 2 pi, that gives you normal frequency f1. That's 100 hertz. f1 is 100 hertz, f2 is 2 kilohertz. So let's see, we can draw the overall Bode plot in this way. Let's see, G0, we can draw G0 volt plot first, 32 dB. So G0 is going to be a flat line because it's constant. So when frequency is changing, it does not change. G0 is going to be exactly at 32 dB straight line. That's G0. G0. And G1. G1 volt plot is also very clear because G1 is a single pole located at omega 1, which is 100 hertz, right? Frequency F1 is 100 hertz. So therefore, we know a single pole has a magnitude volt plot of 2 sections of straight lines. The low frequency section is exactly at 0 dB. The high frequency section is at the -1 slope. -1 slope. And then the intersection point is exactly at F1. F1 we know is 100 hertz, so we can draw at 100 hertz. This is the intersection point. So low frequency straight line, high frequency straight line over here. Okay, so this is the G1 volt plot. G2 is similar. G2 is also a single pole transfer function, but the only difference is that it's located at 2 kilohertz. So therefore, low frequency, let me use maybe another different color to distinguish. Low frequency is flat line at 0 dB. High frequency is -1 slope, and they are intersecting at the F2 frequency, which is 2 kilohertz. So this is the volt plot of G2. Now, we have the volt plot of G0, volt plot of G1, volt plot of G2, and as we discussed, the overall volt plot of the overall transfer function G, which is the product of G0, G1, and G2, would be exactly the magnitude volt plot of G0, G1, G2 adding up together in the volt plot. Okay, these three adding up together, what would be? Adding up together, because this is 0. G2, G, for low frequency, we can start from low frequency. Start from low frequency. You can see there is a G at 32 dB, G1, G2 both at 0 dB. So you add these three things together, that is going to be still 32 dB. So we maintain for low frequency no. Let me use another color. Okay, for low frequency, you can maintain at 32 dB. These three things adding up together, always 32 dB. Until it comes to the first pole frequency, which is 100 hertz. This point. When this first pole occurs, this is changing to, because these three adding up together is going to be G0 does not change, still a flat. G2 does not change, still flat. You can see G1 change to -1 slope. So the overall, adding these three things up together, the overall transfer function is going to be changing to from 0 slope to -1 slope. Okay, and until you see the second pole, the pole of G2 at 2 kilohertz, and here G0 still flat, G1 still at -1 slope, but G2 is now changing from flat to -1. So the total slope is going to be after this point changing to -2 slope. So this is going to be totally -2 slope. So that's going to be the overall body plot, magnitude body plot. It's flat at low frequency, and it has a corner, has a breakover point at 100 hertz. First turning point at 100 hertz, the second turning point at 2 kilohertz. First turning point, after the first turning point, it gets to a -1 slope. After the second turning point, it's changed to -2 slope. So very simple. So this set of approximation methods for transfer function body plots will make the obtaining of the overall transfer function body plot much simpler. Similarly, we can also look at the phase angle. Okay, this picture actually also has a phase angles information. You can see the only difference that it put the phase angle axis on the right hand side. You can see the phase angle axis is put on the right hand side. Okay, let's see. For G0 because it's constant, so therefore G0 has a flat phase angle of 0, always 0. This is a G0 phase angle. This is a G0 phase angle. G1 is a single pole, so therefore the phase angle will be from low frequency 0 degree gradually changing to -90 degrees. And the changing corner frequency of that phase angle would be exactly at F0, which is 100 hertz, okay, over here. So this is going to be G1 phase angle. Remember, 1/10 of F1 and 10 times of F1 are the two turning points for phase angle. Okay. Similarly for G2, low frequency 0, high frequency -90 degree, and in between you use a straight line to connect 1/10 of F2 and 10 times of F2. Okay, so this is going to be a G2 phase angle. And then you add these three lines together, add up together, that's going to be the overall phase angle body plot. Okay, for low frequency, for this part over here, up to here, up to 1/10 of F1, G0, G1, G2, all is located at 0 degree. So add up together, still 0. And then after 1/10 of F1, you see the changing of G1. G1 is changing. So therefore, the overall phase angle of both plot is going to be changing. And then at the 1/10 of f2, at this point, you see another turning point. So therefore, the overall phase angle is also changed to another slope. Okay, and then you see 10 times of f1, another turning over point. Okay, the slope is also changed. And in the end, you see 10 times of f2. That's the overall phase angle of transfer function. So in the end, the total, when you go to the high frequency, the total phase angle of the transfer function is going to be minus 180 degrees, because there are two single poles adding up together. That's going to be totally minus 180 degrees. I'm sorry. So that's a very useful tool to, based on single transfer function, to obtain the overall Bode plot of the overall transfer function. But there's also another issue which is also very useful. So if you know the Bode plot, and you can roughly approximate the Bode plot in combination of straight lines, you are also able to then transfer this Bode plot back to mathematical representation with polynomial representations with poles, a set of poles and zeros in the polynomial. So you can write out the transfer function. So based on Bode plot, write transfer function out. Okay, here is an example. Okay, how to determine the transfer function corresponding to the following symptote of transfer function of Bode plots. Okay, for example, the magnitude Bode plot is in this way. At the low frequency, it is with a magnitude of A0 dB. Okay, and then you see the first turning over point at f1, and then with +1 slope increasing to the second turning over point at f2. Okay, and then correspondingly, you look at phase angle. At low frequency, it is flat, and then it is changing to increasing phase angle, and then it tends to flat again. And then for the high frequency part, it's changing from flat to minus decreasing slope. And then in the end, it stays at 0 degree. So based on these two Bode plot, based on the corresponding magnitude Bode plot and phase angle Bode plot, you will be able to see that this transfer function actually has a low frequency flat, high frequency +1 slope. What is this? And then there are two possibilities. It is either a normal zero, right? Normal zero has a low frequency flat, high frequency +1 magnitude magnitude Bode plot, or a right half plane zero, because the right half plane zero also has a low frequency zero, high frequency part at +1 slope. Okay, that's based on the magnitude. But at the same time, if you look at the phase angle at low frequency is 0 degree, approaching high frequency becomes increasing, positive, changing to positive phase angle. That's normal zero. Ordinary zero, because ordinary zero has 0 has a from 0 degree gradually changing to positive phase angle. Okay, so that means this overall transfer function has a ordinary 0 which is located at f1. And then gradually this slope of magnitude is changing back to flat. That means there's going to be, for magnitude, there is a, for low frequency part is flat, and for high frequency part is decreasing. That means for at this position, there is another transfer function which looks like this. At low frequency, it is flat. It does not affect the slope. But at high frequency, when you come to be much higher than f2, it gives you decreasing slope, so that the overall slope is changing back to flat. So that what kind of transfer function that can give you low frequency flat, high frequency decreasing magnitude both plot? That's normal pole, right? Normal pole has this low frequency flat, high frequency decreasing slope. And if you look at correspondingly to the phase angle, it's also low frequency flat 0 degree, high frequency it gives you minus 90 degree phase angle. Okay, so that means this transfer function must be composed of, if the total transfer function is represented by G, G must be composed of, let's say, one constant. Okay, one constant G0, which is corresponding to the low frequency magnitude dB values, multiplied by G1 and G2. And G1, I can for sure predict that it must be a normal 0, ordinary 0, that has a form of 1 plus s over omega 1, where omega 1 is exactly corresponding to this f1 frequency. And G2 is going to be a normal pole. That means it has the transfer functions 1 over 1 plus s over omega 2, where omega 2 is exactly corresponding to f2. Okay, so based on body plot, I can quickly write out the mathematical transfer function. Okay, and there's some details regarding how to calculate. So that's the important part. One last example I would like to talk about is the quadratic pole. Quadratic pole. On the right hand side, this is the circuit that can generate a quadratic pole response, where you have an input as a voltage source, V1, applied to an inductor, capacitor, and resistor network. And we all know this is a low-pass filter. And if you look at the voltage response across the resistor, V sub 2, and we know V sub 2 over V sub 1, or the transfer function from V1 to V2 can be represented by this polynomial transfer function of 1 over 1 plus SL over R plus S squared multiplied by LC. Okay, that's exactly because the denominator of this transfer function is a second order form. So these are called quadratic pole. Quadratic pole. We will see this also very often in the future. Very typical transfer function you can see. And then, of course, based on what we have learned mathematical method, you can calculate mode plot of magnitude. You can calculate the phase angle. Okay, and then you can also, in the end, use a set of approximation. Very often, we also use two sections of approximation. At low frequency, it is going to be a flat line. At high frequency, it is also a straight line, but this straight line has a slope of minus 40 dB per decade.